Module 2 of the Intro to C Programming course is going to start to go into more of the syntax of writing instructions in the C programming language. And so we're going to go into submodules on variables and writing expressions and using different operators in the C programming language. So let's get started. So the objective of Module 2 overall is to understand how to create variables and what kinds of variables we can create and what kind of program data we can actually store as part of a C program. And then the second submodule, we will go into the discussion of the various built-in operators that we can use to create expressions in C code and how those expressions in C code are going to be interpreted by the compiler in the hopes of manipulating the program data that's stored in our variables and doing something useful. So the first submodule will focus entirely on variables, and this will start from the very foundations of using variables in programming languages. So essentially, the easiest way to think about a variable is it is a placeholder for some sort of information. And conceptually, the easiest way to think about this is it's a box that you put something into. If you think about how you use boxes to put things into, boxes are often designed to hold particular contents. There is a limit to how much stuff we can put into a box. There's a limit to how small of a thing it's meaningful to put into a box. And we know that if we put the wrong kind of contents inside a box, the box might not provide the functionality or the protection that we want. So in other words, the kind of data we want to store kind of determines what kind of variables we want to create to store the data within the system. And this is the foundational idea of a variable. So when we look at a variable, when we think about our analogy of a variable being a box, ideally we want the box to be identifiable because we're going to have a lot of boxes. If we're running a warehouse, if we're running storage, if we just have a closet full of stuff, we don't want to have to go through all of the boxes to find the content that we want. Our boxes should be named. They should be labeled. We should be able to identify this box is not this other box. As mentioned, our boxes are going to hold a particular type of content. Each box might be a little bit different because the content that it's storing is going to be a little bit different. Boxes can have special qualities. And of course, we want to be able to put suitable things into a box and have an expectation that we can recover those contents later and read them and restore them. So this means each of our variables is going to have a name so that we can identify it, a type that describes what kind of contents it's holding, and we can also have qualities that different variables can have. So as an example, suppose I have a box here that stores my favorite toy, and so I label it favorite toy. The type of content, well, it's a toy. So I'm going to put my favorite toy as a special case of type, special type of toy. I might have some particular qualities, like maybe there's a maximum size that my toy can have. Maybe there's some restrictions on how I can interact with this toy. Maybe I'm going to allow it to change over time. And then, of course, I'm going to have a value. So the value is going to be a particular instance of this toy that happens to be my favorite toy. This is a simple conceptual example. Now in C, there are only a certain small number of variable types that can be created, which means the type field is relatively limited. And the very small number of types that are supported by default in the C programming language are what are called the primitive data types. So C supports two different kinds of primitive types. The first one is integer types, and the second one is floating point types. So an integer type is simply a type that stores a variable that is an integer. And in fact, different integer types are going to have different ranges of what they can store. In particular, a different range usually means a different smallest and largest integer that can be stored, which corresponds to different amount of memory that's required to store different sizes of integers. Floating point types are basically variables that represent real numbers, decimal numbers, numbers with a fractional part. And different floating point types will store real numbers to different amounts of precision. And so more bits of storage or more bytes of storage are required to store more fractional decimal places of a real number. So we'll get into this in a little bit more detail, but these are essentially the classes of primitive types within the C programming language. Given these primitive types, we can construct more complicated types, and we will in fact do that in a bunch of different ways, and there are libraries that do this in a bunch of different ways. And so yes, we're limited to these small number of primitive types, but there's essentially no limit to what we can do with them. So the integer types, to go into more detail on the integer types, again, an integer type in C simply stores integer data with no fractional part. And if we want to be able to represent a larger range of integers, we need more bytes of memory. So the different integer types have different sizes based on how much of a range we need to store. Now we can also have special qualifiers on our integer types that say, if I only need non-negative integers, I can actually tell the system that I want what is called an unsigned integer. And if I only need the non-negative values, that's going to give me twice as much range because I don't need to store negative values. If I need to worry about positive and negative values, my range needs to include both positive and negative values, and that's going to take more memory. So I can tell the system through a qualifier, signed or unsigned, whether I want to include the negative side of the range or whether I want a larger but only non-negative range. So there's some flexibility here as well with what kinds of data representations are used and how much memory is going to be used to store those actual variables. So let's look at some of the integer types that are built into C. The first and simplest integer type is a variable type called char, which was originally intended to hold a single ASCII encoded character. Single ASCII character is encoded using 7 bits. And so the intention was to store this in as few bytes as possible, namely 1 byte or 8 bits. So a single signed character can take values in the range of -127 to 127. In some systems, this range is extended to include either 128 or -128. It can't include both because there aren't enough bits. We can only represent 256 unique values using 8 bits. ASCII characters are 7 bits, which means the largest ASCII character is the character value of 127. So when ASCII characters were originally encoded, they were encoded into the values 0 to 127. So this range includes all ASCII characters. If we have an unsigned char variable, that will hold integer values between 0 and 255, because those are all the values that we can represent with 8 bits. So if we were to go ahead and create a char type variable, we can give it a name, we can give it a value, and that value will be interpreted depending on whether our char is signed or unsigned. If we don't specify signed or unsigned, in most systems the default is signed. So if I just create a char variable, the compiler will interpret that to mean I want a signed char variable, and it will know that the value of that variable is supposed to be something between -127 and 127. In this example over here, I have a box holding a character A, In C, ASCII character is denoted by having single quotation marks around it. So single quote A means the ASCII character A, which as an integer is encoded as the number 97, because that's just the ASCII value for that character. So this is a valid representation of a char variable that I've named letter, and I've given it a value of A, or the integer value of 97. I haven't specified whether it's signed or unsigned, so the system is going to interpret it as signed. In this case, it doesn't matter because 97 is in both ranges. The next largest integer type is what is called a short integer, or sometimes just a short. A short integer was originally designed as what's officially called a small integer. A small integer is a 2-byte integer, usually a 2-byte integer. The specification says it needs to be at least 2 bytes of memory. It's almost always 2 bytes in modern systems. With 2 bytes or 16 bits, you can represent 65,536 unique values, 2 to the 16th, which means if you have a signed short integer, or a signed short, that can take values between minus 32,767 up to 32,767. In some systems, it will include either the positive or negative boundary value. That's system dependent. If you have an unsigned short, the range will include all non-negative numbers that can be represented using 16 bits, so 0 up to 2 to the 16 minus 1. Again, in most systems, if you don't specify signed or unsigned, the default will be signed. So if you just declare a short variable or a short int variable, the system will create a signed variable. In this example over here, I've depicted a variable of type short that is unsigned with the name millisec, which here is intended to represent a count of milliseconds for some particular process. The value in the box is 1,267, which is well within the range of an unsigned short. And the value here shown in the value box is actually the same value, just in a different encoding. The decimal value is 1,267. The hexadecimal value is hex 04F3. These both represent the same number, just again in a different encoding. If you actually look into the system memory, computers operate on binary. All of their encodings are using hexadecimal. This is what you'll actually see in memory. This is sort of the human understandable value of that encoding. The next variable type that we have in C is an int. And this is designed to be a normal-sized integer. According to the standard, a normal-sized integer is at least 2 bytes, but usually 4 bytes, which means some systems have different size integers. The vast majority of modern systems use 4 bytes to store integers, standard integers, so 32 bits. With a 32-bit signed integer, we can hold values from approximately minus 2 billion up to 2 billion. With unsigned integers, we can store values exceeding 4 billion. So this is 2 to the 32 minus 1. Again, in most systems, the signed keyword is the default. So if we don't specify unsigned or signed, the compiler will interpret it as signed. Many systems also treat integers as the default. So if you don't actually specify a data type and you just provide a qualifier like unsigned, the compiler will actually know what to do with that. It will interpret unsigned to mean unsigned int. Whether or not that's a good indicator to leave off the type, I don't think it is. I think that's an easy way to make your code less readable. But systems have defaults. So in my example over here, I've depicted a variable of type int that is unsigned. Just like the previous example depicted milliseconds, this example depicts nanoseconds because it's something that I might need to have a much larger number of, larger range. And again, I have a human readable decimal value that can be stored in my variable and the corresponding hexadecimal value, which hopefully is the same if you do the math. In some cases, we actually need integers that are larger than 32 bits. So C also supports what is called a long int. And this is defined as being a large integer. The specification says in memory, a long int needs to be at least 4 bytes. Well, if we go back and look at int is already usually 4 bytes. So in many systems, int and long, or int and long int, are actually the same. And in fact, I verified this on my system. I'll give you a way of verifying this on your own system a little bit later. And you can see how big is an integer, how big is a long. So in this case, long and int are more or less the same, at least on my machine, at 32 bits or 4 bytes. C also gives us one additional integer type, which is called a long int. This is a more recent introduction to the C programming language. This wasn't part of the original C standard. And this was primarily introduced when 64-bit computing came out. So when you have 64-bit computing, addresses in memory can be 64 bits long. And then you need a variable that can store those memory addresses. So a long integer is an 8-byte or 64-bit value. Numerically, a long can hold a ridiculously large integer. If you have an unsigned long, I believe that can store values in excess of 18 quintillion. Numerically, most people don't have uses for integers, for numbers that are that large. So these are often used to represent memory addresses, and then they become very, very meaningful. So the example depicted here is I have a long variable. Its name is address because it's in fact depicting an address. And here you can see that I've used not all of the bytes to even include my address. But we'll see a lot of examples later where these long ints become very useful for us to interpret what the system is doing. All right, let's move on to floating point data types. So again, floating point data types are used to store real values. We're no longer restricting ourselves to integers. We're now looking at real numbers that have a integer component and a fractional or a decimal component. And we need more bytes of memory if we want more significant figures before or after the decimal point. So the encoding that most systems use, the encoding that's part of the C standard, is floating point values are encoded as binary numbers using the IEEE 754 standard. And what the 754 standard says is the encoding of a floating point number includes 3 parts. It includes 1 bit that is used to indicate whether the floating point number is positive or negative. So this is called a sign bit. It has some number of bits that are devoted to representing an exponent and some number of bits that are used to represent what is called the significand, sometimes also called the mantissa or the fraction. So a floating point number has a sign bit S, an exponent X, which is signed, and a significant Y, which is signed. The real value that's represented by this encoding can be computed by this following formula: -1 to the S, 2 to the X times Y. So -1 to the S means that the sign bit, if the sign bit is 0, the real value is positive. If the sign bit is 1, the real value is negative. The use of the exponent X shows up as the exponent 2 to the X, and the significand just shows up as a multiplier. y. So this shows us how we can quickly encode and decode real numbers into a binary encoding. And in memory, when you look at the contents of a floating point, an encoded floating point value, you'll just have s, x, and y in memory. And one bit is used for s, some number of bits are used for x, and some number of bits are used for y, which means the total number of bits that's used for the floating point number is 1, plus however many encode the exponent, plus however many encode the significand. And the interpretation of that is up to the software to work with. So we have 3 different floating point types in C that essentially give us 3 different sizes in memory of this encoding, which means different size of exponents and different size of significand, to give us different numbers of significant figures that we can represent. The simplest floating point type is called float. A float is what is called a single precision floating point number, and the size in memory is usually 4 bytes or 32 bits. With the 32 bits, 1 bit is used for the sign bit, 8 bits are used for the exponent, and 23 bits are used for the significand. And with that encoding, we can get around 7 significant decimal digits of precision, which means on either side of the decimal point, if we go more than 7 decimal digits between the farthest to the left non-zero number and the farthest to the right non-zero number, it gets harder to encode things, and we're going to start having to round off significant figures to be able to store that value in our 32-bit space. So as an example, to evaluate the number of significant digits that you can represent, what people will often do is they'll say, what is the smallest value larger than 1 that can be represented? This is essentially showing 7 significant figures. We can't correctly represent any number between 1 and 1.00000001192, which is 1 plus 2 to the minus 23rd. So as an example, we can look at what happens if we define a constant pi as a floating point number. And one thing you'll see, this is not the actual correct value of the mathematical constant pi. But you get out to about the 6th or 7th decimal place right here where it's correct. 3.141592 is correct. The next digit should be a 6. This is where we're starting to have rounding errors where we can't represent those other significant figures in only 32 bits. But if this is all we need, then we can do this with 4 bytes of storage in memory. If we need more accuracy, more significant decimal digits, we can use larger floating point types in memory. The next largest is called a double. It's called a double because it is double precision floating point. And by double precision, that means we get twice as many significant figures before we start getting rounding errors. It's also double the size in memory. So a double or a double precision floating point encoding is usually 8 bytes in memory, or 64 bits. Of those 64 bits, 11 are used for the exponent, 52 are used for the significand. The length of the significand becomes the important factor in how many significant digits of precision you get. You'll see the 52-bit significand and the 52 showing up down here. That's not a coincidence. When you map it from binary into decimal, you get about 15 significant figures of precision with a double, which means any value with more than 15 decimal digits will be rounded or stored incorrectly. And we can see that with the smallest value larger than 1 that can be represented now has about 15 decimal points of precision. If we need even more precise floating point numbers, which yes, we do actually need more than 15 significant figures sometimes, C also provides what is called a long double. A long double is officially what's called a quadruple precision floating point number. And this uses 16 bytes or 128 bits, with 112 of those bits representing the significand. And again, that shows up down here. And when you do the math into decimal, you get roughly 33 significant figures of precision and in decimal representation of a value. If you need, say, for example, the constant pi to 33 decimal places of accuracy, this is the floating point encoding that you would use, and that would give you significantly more precision in doing sort of fine engineering applications. So these are absolutely needed in some cases. Okay, so those are basically the primitive types. We get a handful of integer types, we get a handful of floating point types, and beyond these, the C programming language allows for us to create other variable types, and these are sometimes called derived types, they're sometimes called custom types. Many derived types have been created and standardized. Many of them are available in libraries that can be included into a C program. A couple of examples to give you. Because the different integer types are not fixed across different computers, that creates challenges for writing code. So there's an entire family of integer types that have been derived with fixed bit length. These are defined in the C standard standard integer library, stdint, and they have names that look like int32 underscore t. Int32 underscore t means this is a integer, signed integer by default, of length exactly 32 bits, and the underscore t is often used to mean derived type or custom type. So this is a 32-bit integer type. There's also unsigned 32-bit integer type, uint 32t. There's int 8t, int 16t, int 64t. And when you use these types, you get a 100% guarantee on the size of that variable in memory, independent of the machine specification, which might tell you that integers are 32 bits or integers are 16 bits, which can vary. So this is a valuable derived type. Another simple type that was introduced in the C99 standard in the late 1990s is a Boolean variable type. Notice there's no Boolean defined in the primitive types in C. So someone actually went and created a library that said, we're going to create a type called bool. We're going to include it in a library, stdbool. It's a standard Boolean library. And this is essentially an unsigned character that can only take values 0 and 1. It's a derived type. It's a special case of an unsigned character. If we assign a value of 2, it's not going to actually have a value of 2. It can only take values of 0 and 1. 0 and 1, in this case, mean false and true. We'll talk more about this and actually show you exactly how this can be done at a later time. But this is a derived type. By default, there is no Boolean variable built into the C programming language. This might make logic operations a little bit tricky for some people, but it turns out Boolean logic is easy to build on top of arithmetic. So we can also have a few additional qualifiers. We talked about the simple qualifiers of having signed and unsigned variables. There are a handful of other type qualifiers that are supported in the C standard. Some qualifiers are only supported in specific C versions. So if you start using more detailed qualifiers, you might be restricting yourself to your code only being runnable by certain compilers. There are a couple of other common type qualifiers that are used. One of them is the const qualifier. Const essentially tells the compiler that this is a constant, and once the variable has a value, that value shouldn't be changed. It shouldn't be allowed to be changed. So this is a special restriction that's put on that variable. Another fun qualifier that you might encounter is the volatile qualifier. We won't talk about this one in this course. It's a fun one when you start talking about systems, because in a system, values can change outside of a program. Some external piece of software or some external stimulus might change values in memory. And volatile is a keyword that tells the compiler that this can actually happen with this particular variable. That's really fun when things happen outside of the visibility of your program, and it means the system needs to be a little bit more careful with the value of that variable. So when we get to actually declaring variables in a C program, the way that we declare a variable is to indicate its type and its name and any optional qualifiers that we want to include. If we want to, we can also assign a value as a part of a declared variable. So this little snippet of code shows declarations of 3 different variables of 3 different types in different ways. Each of these is a valid instruction in C. So they all have to end with a semicolon, because every valid instruction in C ends with a semicolon. The first one simply declares an integer typed variable with the name x. We're not giving any qualifiers. We're also not giving it a value. If we don't give something a value, it is called an uninitialized variable, which means we don't ever want to read the value of this variable because it is uncertain. Before we give it a value, we never want to read from a variable because we might be getting arbitrary residual contents of memory. The second one of these is a floating point type with the name temp. We're assigning it an initial value of 22.1. This is called an initialized variable because it has a value, and now we can read that value. It has meaning. The third example is defining a constant type, a constant double precision floating point type with the name pi, and here we're giving it a numeric value as part of the declaration. So each of these is a way of declaring a valid variable as part of C code. Now, a couple of interesting things. As I mentioned, we're just giving the type, the name, the qualifier, and optionally the value. The value that we're giving, turns out it might not actually be the true value assigned into that variable. Now, you can ask a question of, if I give it a numeric value, why would that not be the value assigned into my variable? And the answer is, I can give it however many decimal places of correct, digits of pi, but the type might not be able to hold all of those correctly. So I'm giving sort of the desired value, but the actual value might be a little bit different. So we need to be careful when we're looking at the numbers that we're giving as the initial values for variables. So these are called literal values. When we give a number, just a numeric value in C code, that's not actually, it doesn't have any kind of type, it doesn't have any kind of name, it doesn't have any qualifiers. It's not actually a variable. It's a literal number. So in C, these are called literals. Now, the compiler will try to interpret literals how we want them to be interpreted. In this case, if we say, take the literal value 22.1, assign it to a floating point variable, it will say, okay, I know how to map 22.1 into a floating point number. I know how to encode that. If we give it this many decimal digits of pi, and we tell it to encode that as a double, it's going to try, but it's going to have some rounding errors. Now we can help if we want to by giving what are called literal type specifiers. I can tell the compiler interpret 22.1 as a floating point number by appending the f on the end of the number. I can tell it interpret this constant as a double value by giving it the long float or lowercase lf literal type specifier. This helps the compiler to get sort of your intentions of what you want it to do with these numbers. Now, you don't have to do this. In some cases it helps, in some cases it doesn't, but this is something that's supported by the language when you're using literals and incorporating and interpreting those literal values as the values of variables. And there are many of these depending on what your variable type is. So the next question we can ask is, what if we assign a value that just doesn't fit the type of the variable that we're trying to assign the value to? So in each of these examples on the bottom, I've done something that's a little bit odd. In the first one, I'm saying declare an integer value, an integer variable called x, and give it a value of 0.5. Well, 0.5 isn't an integer. So what is the compiler going to do? What's the actual value of x going to be? The compiler has to interpret that and try and do something that makes sense. Is this going to be bad? Maybe, maybe not. It depends on what we're trying to assign to what. Another one that we could do, what if I have an integer variable x and I assign an ASCII character to it? What if I create a character value and assign a number outside of the range of a character? What is that going to do? What if I declare a floating point variable and give it a number with way too many decimal digits of precision? What is it going to do? In each of these cases, what it does is actually very straightforward, and we know predictably what a system is going to do because there are rules for how a compiler processes literals and encodes them into different variable types. So feel free to pause the video, think about this for a minute. I'm going to answer what the compiler would do with each of these as soon as I click the mouse. So in this case, if we assign a literal value of 0.5 to an integer, the compiler is simply going to truncate the decimal part of that and store it as an integer. This will be an integer value of 0. If I give an ASCII character to an integer, it's simply going to store the integer value of that ASCII character, which we saw before. The ASCII value of A is the integer 97. If we assign a character a literal value that is much too large for the range of that character, this is a fun one because the compiler is probably actually going to give us a warning. It might not give us an actual error. It might not actually prevent the creation of our executable, but it might give us a warning that says, you're doing something here that is a little bit off. You're going to lose some of your content, but if you're okay with that, I will go ahead and map this number into a character, into the range of a character. And essentially what that's going to do with the value 1499, it's going to end up being a character, a signed character, with a value of minus 37. Why is it minus 37? That's a fun thing for you to figure out. If I give the program a floating point variable f with a lot of precision, it's simply going to lose all of the precision. It's going to truncate this, it's going to round it to whatever it can actually store, and so the stored value in the floating point variable will be 1.0. So this is nothing other than a rounding error. This one, there's no error. This one is a rounding error, and this one is a little bit different, and that's sort of the fun one of these examples. So we do need to be careful to make sure the value fits the type. And there are a lot of ways that we can do this. One of them is what is called typecasting. If we have a variable or a constant, a literal, of a particular type, we can explicitly tell the system to treat it like a different type, and this is called casting. Casting can work in two different ways. If we're going from a variable type of a smaller range to a variable type of a larger range, this can be done without any warnings, without losing any information. We're simply just padding a bunch of bits with zeros. This is called upcasting. For example, if I give you a variable that is a character, the range of a character is a subset of the range of an integer. So if I say, here's a character, store it or treat it like an integer, that's no problem at all. And in fact, that's exactly the example given here. The ASCII A is a character which can take values from -127 to 127. We're telling it to store it as an integer, which can take values -32,767 up to 32,767. The entire range of characters is contained within the range of integers. So everything here is uniquely determined here. And that's why this one is no problem. We're just going to end up with a value of 97. The 3 bytes of additional memory that we're using at the beginning of the integer will be filled with zeros. So that's where the zero padding comes into play. This is upcasting. This should never create a warning. It should never be a problem. And you can actually do it with what's called an implicit cast. We don't have to tell the compiler how to treat this value. It knows what to do, because this is a special case of this. On the other hand, if we're losing information, if we're trying to map a large variable into a smaller range, this is when the compiler knows that we're going to lose information and it might create warnings. The system will try, and it will often try and create a warning. Some compilers will actually fail because they don't want to make assumptions about what you're doing. This is called downcasting. Downcasting is an example of, here is an integer, I want you to treat it like a character. And this is the case in this example. I've given the integer 1,499 as an integer literal, and I'm telling the compiler, treat this like a character. And it's going to say, that might not be a good idea, but I'm going to assume what you want me to do with that integer value. And from 1,499, I'm going to make an assumption that leads to the value of -37. And again, you can figure out exactly what assumption it's making to get from 1,499 to -37. So upcasting is usually not a problem. Downcasting sometimes isn't a problem, but sometimes can be a problem because we are potentially losing information. And losing information is exactly how we go from 1499 to -37. Now, we can do casting implicitly, which both of these examples are, or we can do casting explicitly. Explicit casting, you simply take a value and you put parentheses with a type in front of it. So if I want to explicitly cast the value 1499 into a character variable, I would simply put char in parentheses in front of the value 1499. That's an explicit cast. That's telling the compiler, this is actually what I want to do. Don't give me a warning, just do it. And then the compiler will allow you to do a downcast without potentially throwing a warning. So let's look. I mentioned earlier that we can do a little bit of exploration within a system, since different variable types use different amounts of memory on different systems. C actually includes a function to tell us the size in bytes of an existing variable or of an existing type. So there is an operator in C called the size of operator, and this looks like a function. So the way that this works is I can give it any variable, and it will return to me the number of bytes as an unsigned long integer, the number of bytes that this variable is using in memory on this system. So simple example here, if I define a character, give it a value of a, define an integer, give it a value of -75, I can then go in and say, I'm going to define another variable called size of C, and I'm going to set that equal to the size of the variable C. In all systems, the size of a character is 1 byte, so this is going to have a value of 1. I can then go ahead and say I'm going to create another variable of type unsigned long, name size of x. I'm going to assign it the value, the size of the variable x. In my system, the size of an integer is 4 bytes, so this is going to have a value of 4. And this is how we can actually change the behavior of our code based on the local use of memory within the current system. And we could actually write a bunch of logic that does things differently depending on the size of an integer in the particular local system. Well, this is in fact how libraries that create things like the int32 types, this is how these are created. They have to use the size of operator to create something for you that is necessarily 4 bytes long, because an integer in some systems might not be 4 bytes long. So this is a useful operator that we can start to use to learn about a system. This operator, size of operator, in addition to working on a declared variable, will also indirectly work on a type. So it is legal to call the size of operator on a type rather than on a declared variable. What this is doing is it's called anonymous variable. You're actually declaring a variable without a name, and then you're calling size of on that anonymous variable. It looks like you're calling it on a type. And so you can think of it that way. If you just need to know how big is an integer on my system, you don't have to declare an integer to learn that information. This code just does. Now, for anything else that we really want to do, as we're going through learning about syntax, learning about variables, learning about operators, it's going to be necessary for us to be able to see what we're doing. And in order to be able to see what we're doing, we have to go off on a little bit of a tangent to be able to print variable values. So we're going to go off on a little tangent and look at printing things to the terminal. We already saw in a previous example how to print strings to the terminal. We saw how to print the hello world string, for example. This uses the puts function, which does what is called unformatted printing. It takes a string and directly displays that string on the terminal. Well, now we want to be able to print values of variables. Puts won't actually print the values of variables, it'll only print strings. What we want to do is what is called formatted printing. And so there is a very, very famous function called printf. And we want to learn all about printf, or at least a little bit about printf, so that it can convert variables into strings and print them to the terminal for us. And then that will allow us to inspect the values of our variables and see how things are working internally within our C code. So, at a high level, printf uses what is called a format string. A format string simply says, I want to incorporate the values of some variables into a string, and then I want you to print that string for me. The format string tells printf how to interpret the variables, what types to use, what format to use in converting them into strings, and then whatever other content you want to include. Do you want to print things like new line characters, tab characters, anything else that's part of a string you can print, anything that's printable. You can also change the color of things if you want. The way that terminals print things in color is just to include special format characters as part of a format string, so you can make things colorful and attractive. We don't necessarily care about making things colorful and attractive. It's useful to know that we want to be able to print end-of-line characters, new line characters, or tab characters. We'll use those at times relatively soon. So what the way that the format string in printf works is it says we're essentially going to tell it to convert a variable's value into a literal, into a constant. And we want to print that constant as a string. So we're doing integer to string and floating point to string conversions. And the format specifier is telling printf how to do that. So if we want to include a character, an actual ASCII character, in a string, if we have a char value and we want it to map that into an ASCII character, the format specifier that we use in our printf format string is %c. So %c will go into the format string if we want to embed the value of a character there. If we want to embed the value of an integer, we use %d. If we want it to interpret that integer as an unsigned integer, we use %u. If we want it to encode that as a hexadecimal value instead of a decimal value, we can do %x. There are many other things that we can do. These are just a few. If I have a long integer, I prepend each of those with an L. So this is long decimal, long unsigned. I can also do long hexadecimal, %lx. For long, similarly, prepend it with an L twice. Long decimal, long unsigned. LLX would be long hexadecimal. %f says encode this variable as a floating point variable. By default, it will show a floating point variable, I believe, with 6 decimal places of precision. You can change that. You can put numbers. You can modify this format string. We also have long float for double and long float, or capital L, for long double. These are just ways of telling printf how you want it to interpret values in format string. And I'll show several examples of how this works. Printf turns out has its own manual page in Linux. If you do man3 printf, the 3 here is because there are multiple different versions of printf. There is a printf function in the terminal itself, and we want the printf function for the C programming language. That's what the 3 indicates here. So this will give you the manual page for the C language printf. So examples of using printf. This is sort of the simplest possible example to give. I can declare some variables. I declare a character, a short integer, an integer, and a long integer. I give them names, I give them values, and now I want to print their values to the terminal. So I use printf, I give it a string, which is my format string, and in my format string, anywhere that there is just regular text, that's exactly what's going to print. Anywhere that I have a format specifier, this is telling printf to take the value here and encode it according to this format specifier. So what this line is literally saying is fill in the blank in this string with the variable C, interpreting it as an ASCII character. Fill in the value of this variable here as a decimal value. Again, as a decimal value, as a decimal value. So when you run this, if you have multiple format specifiers in a single format string, you should have that many corresponding variables as parameters to printf. So if I wanted to print 2 values, I would do comma, first variable, comma, second variable, comma, third variable. I could do all of this in one call to printf if I really wanted to. But when I run this, it's actually going to print for me the values that I've requested. So let's go ahead and bring up our terminal and see if we can run this code. So I have, for this particular module, which is module 2.1, I have a program called size.c, var.c for different variables. If we look at var.c, we can see that this is the identical code to what's in our slide right behind it. We're using the printf function. We have our format strings with the different format specifiers. We're including the new line at the end of each of these, so it's going to print 1 string per line because printf will print exactly what we have. If we don't have these new lines, it will print them one after the other on the same line. So this is the code that we want to run. We can compile that, name it var as the output. It compiles correctly. We can run the executable. And when we run it, it simply prints for us character C has the value A, S has the value 17, I has the value -19, L has the value, this very large number. And you'll see that these numbers, in fact, match the numbers in the original literals that we gave as the values for the intended values for these variables. So each of these was encoded correctly, and when we go back and read the value, we get what we expect. Now we can do some fun things with this. We can go and we can modify some of these, and for example, we can look at the prior example that I mentioned. What if we give a way too large of a value for the character C, and then ask printf to print it? We can see what happens. We can compile this, and like I said, this gives us a warning, and it tells us there's overflow, and this changes the value from 1499 to minus 37. This is what I mentioned earlier. But it still works. It still gives us, it's just a warning. It's not a failure to compile, it's actually compiling. And we can run this, but now our character has a value of minus 37, which is not a printable character. And so what we're getting in the output is, I don't know how to print this value. This is kind of a fun example because we're getting a non-printable character. And we're telling it to print as a character. If we don't want it to print as a character, if we want it to actually print the value minus 37, we can say, you know what, don't actually print this as a character, print the integer value. So %d is the integer value of the character. And now we can go in, it'll still warn us about the overflow, but now when we run it, it's going to print for us the integer value minus 37. So this is the role of that format specifier. The format specifier tells printf how to interpret that variable. And in both of these cases, it's the same variable with the same value, but it's interpreting it differently. We're no longer telling it to make it a printable character. Now we're just telling it, make it a number and print the number, because you can always print a number. So this is where printf has value for us. We can start to inspect the contents of our variables, and we can just log them to the terminal to see what they look like. So now we can go into another example. Let me clear this one. We can go into another example, which is a piece of code that looks at the size of operator. And this is a simple piece of code that I wrote, which just calls printf a whole bunch of times and looks at the sizes of different types within my local system, within this virtualized emulated system, Ubuntu 24.04. So it's calling size of for each of the 8 primitive types in C: char, short, int, long, long, float, double, and long double. And so what this is going to tell me is, since size of operates on this type and returns an unsigned long integer, I can simply print an unsigned long integer for each of those values, and I can say the size of a character is some number of bytes. The size of a short is some number of bytes. The size of an integer is some number of bytes. And this is actually querying my system and asking how much memory is going to be used to store each of these types of variables, even though I haven't created any of these types of variables other than just this anonymous call. So this is a great way of characterizing the memory usage in a system for different kinds of variables. So let's go ahead and run this and see what happens. So in my system, what we've just learned is a character is 1 byte, a short int is 2 bytes, an int is 4 bytes, a long is actually 8 bytes. I was wrong about that. I thought a long was 4 bytes. A long is 8 bytes, and a long is 8 bytes. So in this particular system, a long and a long are the same, which is interesting. I was wrong about that. A float is 4 bytes as standardized, a double is 8 bytes as standardized, and a long double, long double is 16 bytes. So this gives us all of the local sizes of our different variables. And one thing that this does, this allows us to profile how much memory is used by our program. Now if I look at this other program and say I created a character, a short int, an int, and a long, I can say, oh, I can add those up, and I just used 15 bytes of memory at a minimum. In actuality, I'm using more memory than that. We'll come back and talk about that later. But this allows you to characterize the memory usage of a program. And you can actually use these numbers, like I said, programmatically. You can use that size of operator to incorporate variable sizes into your code. So the C language is strong enough to be able to do that. All right. So now that we have the ability to print variable values, we can declare variables and print them. This is like the minimum functionality that we need to start doing interesting things. But there's a lot more mechanism that we really need to start doing more interesting things with expressions. So in the next module, we're going to introduce operators so that we can start to do more interesting things and create a variety of interesting expressions that we can freely use to incorporate programmatic logic. We can also create our own operators, and we'll talk about that as well in a bit. But this is going to be the end of this module. And in the next one, we'll start talking about operators.